Welcome you all to this new lesson of circuit theory. In last class, we discussed about some numericals on electric circuits, basic electric circuits. We applied rules of current divider, voltage divider, series parallel combination of resistances. All those we applied to solve some problems, and it was a discussion session. Today we'll be discussing some more problems, more complicated problems in this lesson. So to start with, let us start discussing this problem first. So here you are asked to obtain RAB of this circuit. So equivalent resistance of the circuit is to be obtained if you look back into the network from these two terminals. So now you all are familiar how to get total resistance or equivalent resistance of the circuit. This is one more complicated problem which could be solved by us. So let us solve it step by step. See, suppose in last class also I told you, suppose you have connected two leads of multimeter across these two terminals A and B, you will get a reading of resistance. That reading of resistance will be your overall or total resistance or equivalent resistance of the entire circuit looking back across these two terminals. Okay, so let us start. Let us first, our first step is to mark all the terminals. It will make it more easy for you to understand. So say see, this is C terminal, this is D terminal, this is E terminal, this is F terminal. So these are the nodes which you could mark. Now, see, as I told you before, to find RAB, let us assume that you are initially at point A, you want to reach at point B. So to reach at point B from A, all the resistances encountered will be known as the equivalent resistance of the circuit. Now when you move to point C, there is 16 ohm resistance. But to reach at D from point C, see, you will find two paths, two different paths. One is of 20 ohm path, another is of 5 ohm path. So what you need to do, these two are connected in which combination? Parallel, because starting point and ending point of 20 ohm is C and D. Starting and ending point of 5 ohm is also C and D. So in both cases of these resistors, starting and ending points are same. Hence, we can conclude that these two are combined in parallel. So if we redraw the circuit, this is A terminal, this is C terminal. Now combining these two, 5 and 20 in parallel, it will be 20 into 5. Divided by 20 plus 5, that is 25, which gives us equivalent resistance of 4 ohm. So, so these two parallelly combined resistors can be replaced by 5 ohm. So this red marked resistance is showing that this is parallel combination of these two resistors. Now, from D to E, there is one 1 ohm resistance. So this is D point. From D to E, there is 1 ohm resistance. Okay. Now from E to F there is 2 ohm resistance. From E to F there is 2 ohm resistance. Now C to F there is 9 ohm resistance, and between C and F and B there is no resistance connected. Between C and B there is 18 ohm. This is 16 ohm. Okay. Now what can you conclude here? Acha, between C and D there is 20 ohm resistance. Now, now see, uh, A and C, in between A and C there is 16 ohm. Between C and D there is a 5 ohm. And between D and D there is 1 ohm. Now, this is a single path. This is a single path to reach at E from C. So, so what can we say? That in between C and D there is 5 plus 1, 6 ohm, and in between C and D there is 20 ohm. So this can again be drawn like this. This is A, this is 16, this is C. Now between C and D there is 120 ohm, and between C and D there is one combination of 5 and 1 ohm series. So this combination will be 6 ohm. This is 6, this is 20. Now see, now see, B and F, these two are having no resistance connected in between. That implies B and F can be considered as a single point. So between B and F can be considered as a single point, same point. So between B and F there is nothing connected, but between E and F there is 2 ohm. So E and F there is 2 ohm. Between C and B there is 18 ohm. This is 18 ohm. So, so what can we conclude from this is, now now from this we can get this one. This is A. Between A and C there is 16 ohm. Between C and E there is 120, 16 ohm. Okay. Now 20 and 6 will be parallel. Between from C to E you can follow 20 ohm path, you can follow 6 ohm path. So these two are in parallel. So 20 parallel 6 means 20 into 6 divided by 26. Okay, so this will give us 60 by 30. So in between C, this is C, and in between E, between C and E, there is 60 by 13 ohm resistance. So this is parallel combination of these two. Now between E and F, there is, this is B or F, there is 2 ohm, and between B and C there is 18 ohm. Now, now see, now let us delete this part. Now again let us redraw the circuit. This is A, there is 16 ohm, this is C. Now in between C and B there is one 18 ohm, in between C and B or F, in between C and B there is one 18 ohm, and between C and B 60 by 13 and 2 are connected in series. So 60 by 13 plus 2. This is series combination of 60 by 13 and 2. Will give us 13. Here it will be 86. So between C and B or F, there is 86 by 13. Now it is clearly understood that in latter case, what will happen? These two resistors will be in parallel. With that parallel combination, 16 will be in series. So RAB can be given by 16 plus 18 parallel 86 by 13. So to get this parallel combination, we'll use the formula R1 R2 by R1 plus R2. With that combination, 16 is in series. So this is how you can get the overall or equivalent resistance across AB terminals. Now let us move to next problem. Here in this problem, we are asked to determine the value of VAB. This is A point, this is B point. Find out voltage across A and B. If we redraw the circuit will look like, see, this is the supply. In between supply, there is R2 and R3 connected in series. So this is one path. So you can redraw it like this. Okay, and this point is, see, from supply positive there is 50 ohm, from supply positive there is 50 ohm. 50 ohm is connected to B point, 50 ohm is connected to B point. From B there is 200, which is again connected to supply negative. From B there is 200, which is again connected to supply negative. So this is one path. Another path is this one. From supply there is another path like this. So from supply positive there is 100 ohm, and from the 100 ohm there is point A. So this is point A. From point A there is 300 ohm, which gets connected to negative. So this is 100 and this is 300. Now this voltage is 40 volt. Now what can we do? As supply, this entire branch and this entire branch are connected in which combination? All these three are connected in parallel combination. Suppose this is X point and this is Y point. So supply is connected between X and Y. This branch is connected between X and Y, and the right branch is connected between X and Y. So all these three are connected in parallel, we could say. Okay. Now, as these are connected in parallel, so voltage across this series branch 50 and 200, these are connected in series. So voltage across this series branch is 40 volt. So the 40 volt will appear across this series branch. Okay. Now, where this point is, B point. So suppose this is Y point and this is X point. So what should be VBY? Voltage across BY is voltage across 200 ohm. So VBY can be written as per voltage divider rule. Total voltage is 40, which is appearing across 250 series combination. So total voltage multiplied by, we are going to find VVY, that is voltage across 200 volt. So that resistance will be there here. By sum of the resistances, 200 plus 50, that is 250. So by cancelling this, it will be 5, it will be 4. So 8 into 4, 32 volt. So VB is 32 volts. Clear? Now, as all these are connected in parallel, so we could say that voltage across 100 ohm and 300 ohms series combination is also 40 volt, and this point should be A. So as per voltage divider rule, VA, this is A point, this is Y point, so VAY means voltage across 300 ohm. So VAY equals to total voltage 40 multiplied by 300 by 300 plus 100, that is 400. So 3 by 4, 10, 34. So now we are asked to obtain VAB. Can we write VAB equals to VAY minus VBY? Y is at ground potential. So actually VAY means VA and VBY means VB. So VAB equals to VA minus VB. So this should be leading to minus 2 volts, which implies voltage across A and B terminal will be 2 volt with B positive. B is more positive with respect to A. That is why we have got minus 2 volts. Okay. See here, VAB means voltage across this with A positive considered, but we have got VAB equals to minus 2 volt. That implies, minus sign implies A is at lower potential than B. Okay. So this solution is being given here, which we discussed earlier. Now let us move to next point. Okay. We are asked to obtain VAB for this Wheatstone bridge. These Wheatstone bridge type configurations are very frequently used in electric circuits. For practical circuits, Wheatstone bridges are very popular. Find VAB of the circuit. We are asked to obtain VAB of the circuit. Resistances are given 55, 200 and RX. Now it is given that consider RX is replaced by a short circuit. So if Rx is replaced by a short circuit, what will happen? See, there is one path through this, there is another path through this. So this can be redrawn as, see, E. Now E is connected, E positive terminal of E is connected to one terminal of R1. So positive terminal of E is connected to one terminal of R1. Similarly, positive terminal of E is also connected to one terminal of R2. Similarly, it's also connected to one terminal of R2. Negative R1, another terminal of R1 is connected to R3. Another terminal of R1 is connected to R3. The junction of R1 and R3 is given by A node. So junction of R1 and R3, junction of R1 and R3 is given by A node. Similarly, another terminal of R2 is connected to Rx. Another terminal of R2 is connected to Rx. The in between junction is given by B. Now R3 and Rx both are connected to negative terminal of supply. R3 is connected to negative terminal of supply. Rx is also connected to negative terminal of supply. Now, it is given that if Rx is replaced by a short circuit, so this Rx here replaced by a short circuit, so there is no resistance in between. If Rx is replaced by short circuit, what will be VAB? So as like last problem, VA could be found out using voltage divider rule. E combination of R1 and R3, combination of R2 and Rx, all are connected in parallel. So voltage across A, voltage at A point is voltage at A with respect to ground. So any voltage should be measured with respect to ground. So VA equals to voltage across 200 ohm. So total voltage is 10 multiplied by, as per voltage divider rule, 200 divided by 50 plus 200, that is 250. So 5, 4, so 8 volt. So VA is found 8 volt. Similarly, let us find VB. See here, B point, listen carefully. B point is shorted with the ground potential. This negative terminal means ground potential. So B point is shorted with ground potential. So suppose you have 10 volt here. Now if it is connected to point X, then what would be voltage at point X? Same, because if there is nothing connected in between, those 2 points can be considered as same point. So as Rx is 0, that means this terminal is shorted. So B and negative terminal of supply both will be at same point. So negative terminal of supply voltage will have 0 volt. Consequently, VB will have 0 volt. So what will be VAB? VAB will be equals to VAB equals to VA minus VB, that is equals to 8. VA equals to 8, VB equals to 0. So this would be 8 volt. Okay. So there is a small trick given here which makes the problem more easy, that we don't need to apply any voltage divider rule here to find it out. For cross check, you can also find VB using voltage divider rule. Total voltage is 10. You are finding voltage of B point. So B point and ground, in between these two, zero resistance is connected. So it will be 0 by 0 plus 5 kilo ohm. That is 5,000. 5 kilo ohm means 5,000 and 0 ohm means plus 0. So it will be 0. Okay. So this is how you can solve complex problems using applying current divider, voltage divider, all these rules. Now, as of now, what we discussed in theory, we have applied all those theoretical knowledge, applied all the rules to solve critical problems. But if you have some more critical problems in which the circuit elements are not simply involved in series parallel combination, in those cases, current divider or voltage divider rules alone will not be effective to get the result. So in that case, what shall we do? We must apply Kirchhoff's voltage or current law to get the solution. So in next class, we'll be discussing about Kirchhoff's current law and voltage law, and how can we apply those laws to solve practical circuits which does not have only the series parallel combination of resistances, which may involve some other combinations. So if a circuit is having only series parallel combination of its elements, then we can apply current divider, voltage divider rule, uh, source transformation, basic rules we can apply. But for the more complex circuits which does not involve only series parallel combination, we must apply Kirchhoff's law. And Kirchhoff's laws are, there are two types, two Kirchhoff's laws. One is related to current, Kirchhoff's current law, another is Kirchhoff's voltage law. So those two laws will be discussed in next class. So I'm ending up here today. Meet you in the next session with Kirchhoff's voltage law and current law. Thank you all.